Imagine a force that cannot be seen, touched, or heard. Yet its influence is woven into the very structure of the universe. It shapes galaxies, sculpts the birth of stars, protects planets, and guides the furious outbursts of black holes. This force doesn't emit light or sound. It doesn't announce itself with grand theatrics. Instead, it whispers in the silence of space, arranging matter and energy with quiet precision. It is the magnetic field, one of the most pervasive, mysterious, and transformative forces in the cosmos. In this first chapter of our journey through the magnetic universe, we explore what magnetic fields truly are, where they come from, and how they invisibly shape the grand architecture of everything we know. At its heart, a magnetic field is a region of space where magnetic forces act. These forces emerge whenever electric charges move, whether it's a current through a wire or particles spiraling at relativistic speeds through the vacuum of space. But this simple definition belies the profound significance of magnetic fields across scales, both atomic and cosmic. Every star, every planet, and even the vast voids between galaxies are imbued with magnetic fields, like unseen scaffolding. They thread through molecular clouds, sweep across spiral arms, wrap around black holes, and reach out into the intergalactic medium. They act as a silent blueprint, a hidden code embedded in the structure of the cosmos. And yet, despite their omnipresence, they remain invisible to our eyes. We detect their influence only indirectly through the light they polarize, the particles they accelerate, or the delicate dance of plasma they orchestrate. This is the paradox of magnetic fields. They are everywhere, and yet they must be inferred, reconstructed from the signatures they leave behind. Where magnetism begins. To understand where magnetic fields come from, we must begin at the smallest scale, the movement of charged particles. When an electron or proton moves, it generates a magnetic field. When countless particles move together like the molten iron churning in Earth's outer core, or plasma swirling in a young star, they create organized, large-scale magnetic fields that can persist for billions of years. This process is known as the dynamo effect. In rotating, electrically conductive fluids, the movement of particles generates electric currents, which in turn produce magnetic fields. These fields can feed back into the system, sustaining and amplifying themselves. It is a self-organizing phenomenon, where motion gives rise to force, and force reshapes motion. But the story doesn't start with planets or stars. Some scientists believe that magnetic fields may trace their origins all the way back to the beginning of time, to the inflationary epoch of the Big Bang. In those first fractions of a second, when space itself expanded faster than the speed of light, quantum fluctuations could have seeded tiny magnetic irregularities. Though feeble, these primordial magnetic fields may have been stretched and magnified across the universe, acting as the first magnetic imprints in a young cosmos. Magnetism as cosmic memory. One of the most elegant truths of the cosmos is that energy never disappears. It only changes form. Magnetic fields are a living memory of motion, fossilized into structure. They are records of rotation and turbulence, traces of collapse and expansion, echoes of cosmic violence and gentle order. In galaxies, these memories take form as structured magnetic fields aligned with spiral arms. As the galaxy rotates, its magnetic field is sheared and stretched, twisting into elegant helices that trace the curvature of stellar orbits. In star-forming regions, magnetic fields guide gas along filaments like invisible rails, concentrating matter where stars can be born. Even in the largest structures, we know galaxy clusters and the cosmic web magnetic fields are present. Intergalactic filaments stretch across millions of light years. And though their magnetic fields are faint, they are real. These fields shape the flow of matter across the universe and may help explain how cosmic rays, the high-energy messengers from deep space, traverse such vast distances. The magnetic shield of Earth. Closer to home, magnetic fields play a far more personal role. Earth's magnetic field, our planet's invisible guardian, shields us from the relentless assault of solar and cosmic radiation. Without it, the solar wind would strip away our atmosphere, leaving Earth as barren as Mars. Generated by the dynamo in Earth's liquid outer core, this geomagnetic field forms a bubble called the magnetosphere, deflecting charged particles and channeling some toward the poles. There, the collision of solar particles with our atmosphere creates the auroras, those luminous curtains of green, pink, and violet that dance above polar skies. They are the most visible expression of the magnetic field's protective role. Beautiful, ethereal, and vital. But the Earth's magnetic field is not static. It wobbles, reverses, and pulses over geological timescales. Magnetic poles flip, weaken, and migrate. These shifts are reminders that even the most seemingly stable structures in nature are dynamic, alive with internal motion. The magnetic lives of stars. Stars, too, are magnetic creatures. Within their fiery hearts, convective layers churn and rotate, generating magnetic fields that wax and wane in cycles. Our own sun experiences a roughly 11-year magnetic cycle, during which sunspots, solar flares, and coronal mass ejections rise and fall in intensity. These magnetic storms hurl vast quantities of plasma into space, sometimes striking Earth and disrupting satellites, power grids, and communications. Solar magnetism is not merely an academic curiosity. It is a force that tangibly touches our technological civilization. Massive stars, nearing the end of their lives, may intensify their magnetic fields to extreme degrees. In their death throes, they can collapse into neutron stars or black holes, objects where magnetic fields take on staggering proportions. The remnants of stellar magnetism in these objects can shape the behavior of matter and radiation in ways we are only beginning to understand. A magnetic thread through time. From the early whisperings of quantum fluctuations to the modern cry of radio pulses from distant galaxies, magnetic fields thread through the entire story of the cosmos. They are not merely side effects or curiosities, they are participants, sculptors, and archivists of cosmic history. Every region of space bears the fingerprint of magnetism. Some fingerprints are bold and etched like those of pulsars or magnetars. Others are subtle, woven into the background like the faint fields in cosmic voids. But all of them are part of a deeper story, one in which the motion of matter, the twisting of fields, and the rise of structure are intimately linked. To understand magnetic fields is to understand how the universe organizes itself, how chaos becomes order, how collapse becomes creation, how silence becomes music. Galactic magnetism, the architecture behind the arms. In the grand architecture of the universe, magnetism is a silent thread, a force that neither dazzles like starlight nor deafens like explosions, but one that shapes, protects, and organizes on scales both intimate and infinite. It moves unseen, yet leaves a signature in everything, from the graceful sweep of a galaxy's arms to the auroras that dance over polar skies. If gravity is the sculptor of form, then magnetism is the composer of motion and rhythm. It guides, it channels, it shields, and in this part of our journey, We trace its influence through the luminous spirals of galaxies and into the very cores of planets, where swirling metals whisper their secrets in magnetic tongues. This is a story of cosmic weavings of how galaxies breathe with magnetism and how planets, like Earth, live beneath its invisible wings. Look up at the night sky and behold the Milky Way, a glowing swath of light arcing from horizon to horizon. This seemingly tranquil vista hides the intricate dance of charged particles and invisible forces in galaxies. Magnetic fields are not mere passengers, they are partners in motion. They trace the spiral arms, entwining themselves with gas, dust, and light. Though far weaker than Earth's field, typically just a few microgauss, these galactic magnetic fields stretch across tens of thousands of light years, subtly orchestrating the rhythm of cosmic life. But how does such a delicate force arise on such enormous scales? At the heart of every galaxy lies chaos, clouds of ionized gas swirling, stars being born and dying, supernova shockwaves sweeping across interstellar space. Amidst this turmoil, a dynamo effect unfolds. Charged particles in motion generate currents, and those currents, in turn, produce magnetic fields. This feedback loop, amplified by turbulence and rotation, is what transforms faint, primordial seed fields into the vast magnetic tapestries we observe today. In spiral galaxies like our own, the magnetic field lines often align with the arms, as if following the galaxy's rotational flow. This alignment isn't random. It's evidence of how motion sculpts magnetism. As the interstellar medium rotates, it stretches and twists the field lines, shaping them into coherent, large-scale structures. These magnetic patterns help stabilize gas clouds, prevent them from collapsing too quickly, and even regulate where and when stars can form. The very shape of a galaxy is inseparable from the forces that bind it, and magnetism is one of them. High-energy particles, known as cosmic rays, zip through the universe at nearly the speed of light. They are born in violent places, exploding stars, black holes, supernova remnants. But despite their energy, their journey is rarely straight. Galactic magnetic fields catch them like a net, forcing them to spiral, scatter, and reroute across the interstellar medium. This behavior does more than delay their arrival to our detectors. It changes the story of how energy is transported through galaxies. Magnetic fields confine cosmic rays, trapping them within galactic disks, where they interact with matter and light, influencing heating, ionization, and chemical evolution. They become more than particles. They become messengers carrying energy, triggering reactions, and lighting up the sky through synchrotron radiation. Synchrotron radiation, emitted when cosmic rays spiral along magnetic field lines, gives us a way to see the invisible in radio wavelengths. These signals reveal the structure and strength of galactic magnetic fields, offering astronomers a window into their elusive patterns. How do we study something we cannot see? Light holds the key. When light passes through a magnetized medium like a cloud of interstellar plasma, it gets twisted. This effect, known as Faraday rotation, changes the polarization angle of light depending on the strength and orientation of the magnetic field along the line of sight. By studying these twists, astronomers can map the otherwise hidden architecture of magnetism. Another method lies in observing polarized starlight. Dust grains in interstellar space tend to align themselves with local magnetic fields, causing the light that passes through them to become polarized. Measuring this polarization allows scientists to deduce the direction of the magnetic field projected on the sky. Together with Faraday rotation, these techniques build a three-dimensional view of cosmic magnetism. With modern radio telescopes like the Very Large Array and the upcoming Square Kilometer Array, we are poised to unravel these invisible threads in unprecedented detail. Each data point, each polarized signal, adds a brushstroke to the vast canvas of the cosmic magnetic web. Closer to home, magnetic fields take on a more personal meaning. Earth's magnetic field is not just a scientific curiosity, it is a shield, a sculptor of habitability, and the quiet protector of every breath we take. Generated deep within the outer core, where molten iron and nickel churn in slow, convective motion, our planet's magnetic field emerges through the dynamo effect. The movement of conductive material creates electric currents, and those currents, looping through the planet's interior, produce a magnetic field that extends thousands of kilometers into space. This magnetosphere deflects the solar wind, a stream of charged particles from the sun that could otherwise strip our atmosphere and sterilize the surface. Without this shield, Earth might resemble Mars, dry, cold, and barren. Instead, we have a sky that dances. The auroras, those curtains of green and violet light that ripple above the poles, are born from this interaction, when solar particles are funneled by the magnetic field toward Earth's upper atmosphere. They collide with oxygen and nitrogen, igniting light. It is a cosmic ballet. The sun's fire meets Earth's magnetic grace. Each planet tells a different story of magnetism. Jupiter, the giant, hosts the most powerful magnetic field of any planet in our solar system, generated by a core of metallic hydrogen under immense pressure. Its magnetosphere extends millions of kilometers, enveloping moons like Io in radiation belts and sparking intense auroras far beyond Earth's scale. Mars, by contrast, is a planet that lost its voice. Once, it may have had a global magnetic field, but it vanished billions of years ago. Today, only remnant crustal fields remain, a patchwork of magnetism embedded in its rocks. Without a strong magnetic shield, the solar wind has gradually eroded Mars's atmosphere, leaving behind the thin veil of gas we see today. Venus, so similar to Earth in size and composition, offers another paradox. Despite its similarities, Venus has no global magnetic field. Its slow rotation and perhaps the absence of a convecting metallic core prevent the dynamo from forming. The result, Venus faces the sun's fury largely unprotected, and its thick atmosphere, while still present, bears the scars of ion loss and solar stripping. These planetary contrasts underscore a vital truth. Magnetic fields are not mere adornments, they are determinants. They shape a planet's atmosphere, surface conditions, and ultimately, its ability to support life. What makes a planet habitable? Liquid water, a stable climate, the right chemical ingredients, all are essential. But above them all stands an invisible requirement: a magnetic field. Without it, a planet's atmosphere may not survive. The solar wind, relentless and charged, strips away molecules unless something pushes back. Earth's magnetic field plays this role. It has held our atmosphere close for billions of years, allowing oceans to form, life to flourish, and oxygen to accumulate. Mars lost that battle. Its magnetic silence speaks volumes. The water it once held, now frozen or escaped, was a casualty of its vulnerability. Its potential for life, once real, was curtailed not by distance from the sun or the absence of carbon, but by the quiet loss of its shield. And so, in our search for life beyond Earth, magnetic fields may become a crucial filter. A distant exoplanet may orbit in the habitable zone, may have oceans, even continents, but if it lacks a magnetic field, it may also lack the time and protection necessary for life to take hold. Galaxies and planets are not islands. They are knots in the grand tapestry of the cosmos, connected by magnetism threads of influence and structure, from the arms of spiral galaxies to the iron hearts of terrestrial worlds. Magnetic fields weave through time and space, whispering the rules by which stars are born, planets are shielded, and life fleeting and fragile may find a place to begin. We have only begun to understand these threads. With each new telescope, each signal twisted by Faraday's hand or lit by synchrotron glow, we draw closer to the truth that in a universe of light and gravity, magnetism is the quiet force that holds the music together. Magnetic fields in starbirth and cosmic jets. In the silent shadows of nebulae and the glowing hearts of newborn stars, magnetism whispers its influence. It is an unseen hand guiding the genesis of stars, threading through the dense clouds of gas and dust, sculpting the very architecture of cosmic nurseries. Here, in these quiet, luminous cradles of creation, magnetic fields play a role so vital, so intricate, that without them, the stars we gaze upon each night might never have come to be. And yet, their work doesn't stop at birth. Across vast gulfs of space, in the blazing throats of black holes and neutron stars, magnetism becomes a force of dramatic spectacle, launching cosmic jets that stretch across galaxies, shaping the dynamics of galaxies themselves. Let us begin in the heart of the molecular cloud, a region of interstellar space rich in hydrogen, cool and dark, yet primed with potential. These clouds are the raw material for stars, the cocoons where gravity battles against pressure and magnetic tension to ignite nuclear fire. For decades, astrophysicists have studied these regions, puzzled by a profound question: how does such a massive cloud collapse into a dense, luminous star without spinning itself apart in the process? The answer, in large part, lies in magnetic braking. As a molecular cloud collapses, it inherits angular momentum from its rotation, which, if left unchecked, would cause it to flatten and fragment chaotically. But magnetic fields act as regulators, like cosmic brakes. They channel angular momentum away through Alfvén waves, ripples of magnetic energy carried through plasma, allowing the cloud to contract in a controlled, stable fashion. Without this magnetic dissipation, star formation would be inefficient, unstable, and chaotic. It is the magnetic field that ensures a quiet orchestration, a slow, measured descent toward fusion and light. But magnetic fields are not passive observers. They also act as dynamic participants. Within collapsing clouds, magnetic field lines thread through filaments of gas, aligning with the flow of material, directing it inward toward gravitational centers. Observational studies using polarized light from dust grains. Tiny, irregular particles that align themselves with magnetic fields have confirmed this alignment. These observations, enabled by instruments like the Planck satellite and the James Webb Space Telescope, reveal a sky not just full of stars, but interwoven with invisible lines of magnetic structure. This magnetic alignment does more than guide gas. It helps regulate fragmentation, determining how many stars will form and how closely they will cluster in high-mass star-forming regions. Magnetic fields can resist the turbulent forces that would otherwise tear clouds apart, enabling the formation of massive stars that seed their environments with heavy elements and energize their surroundings with ultraviolet radiation. Yet even as they birth stars, magnetic fields can store and suddenly unleash immense energy, one of the most fascinating processes in astrophysics. Magnetic reconnection occurs when twisted and sheared magnetic field lines snap and reform. releasing tremendous energy in the process. This phenomenon, well known in solar flares on our Sun, also occurs in star-forming regions and young stellar objects, injecting localized heat into the cloud and altering ionization states that affect the chemistry and collapse dynamics. Reconnection is not just a violent outburst, it's a sculptor's chisel, subtly shaping the pace and pattern of star formation by heating local pockets of gas. It can create temperature gradients that influence where and when stars emerge. In highly magnetized environments, these reconnection events may even generate outflows jets of material expelled at high speed from young protostars that carve cavities in their natal clouds and regulate further accretion of material. These protostellar jets, small cousins of the colossal relativistic jets seen from black holes, represent another triumph of magnetism, though far less energetic than their supermassive counterparts. They obey similar physics as material accretes onto a young star from a surrounding disk. Magnetic field lines are wound into a helical shape by the star's rotation. This twisted configuration channels a fraction of the infalling material outward in a narrow, collimated stream. Observations of Herbig-Haro objects, shock fronts where jets slam into surrounding gas, testify to the violent precision of this process. In these jets, the interplay between magnetism and plasma dynamics becomes vivid. The jets are magnetically dominated, meaning that the magnetic pressure exceeds the thermal or kinetic pressures of the material. This dominance provides stability, allowing the jets to travel vast distances, sometimes light years, without dispersing. Like needles of fire stitched through the interstellar fabric, they pierce the darkness with order and energy. And as with stars, so too with the monsters of the cosmos, around neutron stars and black holes, where gravity becomes extreme and space-time bends toward infinity. Magnetic fields once again take the lead, accretion disks dense. Hot rings of matter spiraling inward generate powerful magnetic fields as ionized particles move at high speed. These fields don't just guide the infall of matter, they can extract rotational energy from the central object itself. In the case of black holes, this occurs via the Blandford-Znajek mechanism. Here, twisted magnetic field lines tap into the rotational energy of a spinning black hole, launching jets of plasma outward along the poles. These jets are among the most luminous and powerful structures in the universe, visible across billions of light years. Their synchrotron radiation light, emitted by charged particles spiraling in magnetic fields, reveals the structure and dynamics of the field itself, like ink revealing the shape of invisible currents. Neutron stars, particularly pulsars and magnetars, also drive jets. In these environments, magnetic fields reach titanic strengths, bending atomic structures and warping space itself. The fields around magnetars are so intense they can trigger starquakes, fractures in the crust of the neutron star caused by magnetic stress, which in turn release bursts of gamma rays. These outbursts are among the brightest events observed in the universe. Cosmic jets, whether from infant stars or ancient black holes, are not merely byproducts, they are sculptors in their own right. The energy they inject into the surrounding environment can heat interstellar gas, inhibit or trigger star formation, and enrich the medium with metals. In galaxy clusters, supermassive black hole jets help regulate cooling flows, preventing runaway starbursts that would otherwise destabilize galactic cores. In this grand ballet, magnetic fields provide choreography. They maintain order in chaos, channel the fury of collapsing clouds, and tether the raw energy of spinning singularities. They are the weavers of jets, the governors of angular momentum, the invisible guides of stellar destiny. Yet, for all their power, they remain elusive, measurable only through their influence on light and matter. We trace them through polarization, infer their presence from synchrotron radiation, and map their twists through Faraday rotation. They speak to us not in words, but in orientation, acceleration, and spin. Our understanding of magnetic fields in starbirth and cosmic jets is still growing. Every observation, every simulation, every moment when a telescope captures a jet slicing through the void or a protostar firing a burst of plasma tells a deeper story of how magnetism shapes the universe. Magnetism in exotic objects, white dwarfs, neutron stars, and magnetars. In the vast tapestry of the cosmos, certain celestial objects stand out not just for their brilliance, but for the enigmatic magnetic forces they harbor. White dwarfs, neutron stars, and magnetars, stellar remnants of once mighty stars, are laboratories of extreme physics, where magnetism reaches unfathomable intensities. These compact objects, though diminutive in size, wield magnetic fields that challenge our understanding of matter, energy, and the very fabric of space-time. White dwarfs are the dense cores left behind after low to intermediate mass stars exhaust their nuclear fuel, typically about the size of Earth, but with masses comparable to the Sun. These stellar remnants are composed mostly of electron-degenerate matter, while many white dwarfs are relatively quiescent. A subset exhibits magnetic fields ranging from a few kilogauss to over a gigagauss up to 1 billion times stronger than Earth's magnetic field. The origin of these intense magnetic fields in white dwarfs has been a subject of debate. One prevailing theory suggests a fossil origin, where the magnetic field is a remnant from the progenitor star, amplified during the star's collapse. Another hypothesis involves binary interactions, where the merger of two white dwarfs or accretion from a companion star could generate a dynamo effect, amplifying magnetic fields to observed levels. Recent studies have also proposed that internal processes during the cooling of the white dwarf itself might play a role in magnetic field generation. A particularly intriguing discovery is that of white dwarf pulsars. These are white dwarfs that exhibit pulsar-like behavior, emitting periodic bursts of radiation due to their rapid rotation and strong magnetic fields. The identification of such objects blurs the line between traditional white dwarfs and neutron stars, suggesting a continuum of magnetic phenomena across different stellar remnants. When massive stars undergo supernova explosions, their cores can collapse into neutron stars objects so dense that a single teaspoon of their material would weigh billions of tons. These neutron stars often possess magnetic fields trillions of times stronger than Earth's, making them some of the most magnetic objects in the universe. Pulsars, a type of neutron star, emit beams of electromagnetic radiation from their magnetic poles. As the star rotates, these beams sweep across space, and if aligned correctly with Earth, they can be detected as regular pulses, hence the name pulsar. The mechanism behind this emission involves the acceleration of charged particles along magnetic field lines, producing radiation across the electromagnetic spectrum. The geometry of a pulsar's magnetic field is complex. The magnetic axis is typically inclined relative to the rotation axis, leading to a lighthouse effect as the star spins. Models of pulsar magnetospheres consider various regions where particle acceleration occurs, such as the polar cap, slot gap, and outer gap. These regions are crucial for understanding the emission mechanisms and the observed pulse profiles of pulsar. Among neutron stars, magnetars stand out for their colossal magnetic fields, which can exceed 10^15 Gauss. These fields are so intense that they can distort atomic structures and influence the properties of the vacuum itself. Magnetars are relatively rare, with only a few dozen confirmed in our galaxy, but their extreme magnetic environments make them subjects of intense study. Magnetars exhibit a range of high-energy phenomena, including sporadic X-ray bursts, giant flares, and persistent X-ray emission. These events are thought to be powered by the decay and reconfiguration of the magnetar's magnetic field. For instance, sudden shifts in the magnetic field can fracture the star's crust, releasing vast amounts of energy in the form of X-rays and gamma rays. One of the most intriguing aspects of magnetars is their potential connection to fast radio bursts. Fast radio bursts are millisecond-long bursts of radio waves originating from distant galaxies. While their exact origin has been a mystery, recent observations have linked some FRBs to magnetar activity. In 2020, a bright radio burst was detected from the galactic magnetar SGR 1935+2154, providing compelling evidence for this connection. The mechanisms behind fast radio bursts emission from magnetars are still under investigation. One model suggests that crustal fractures in the magnetar generate ALMA waves, magnetohydrodynamic disturbances that propagate through the magnetosphere, leading to coherent radio emission. Another theory involves magnetic reconnection events, where twisted magnetic field lines snap and reconnect, releasing energy that powers the radio bursts. To probe the extreme environments of magnetars and other compact objects, astronomers rely on space-based observatories like NASA's Chandra X-ray Observatory and the Nuclear Spectroscopic Telescope Array. These telescopes provide high-resolution X-ray observations, crucial for studying the high-energy emissions from these objects. Chandra's observations have revealed detailed structures in magnetar magnetospheres, including hotspots on the star's surface and extended emission regions. Nuclear Spectroscopic Telescope Array, with its sensitivity to higher energy X-rays, complements Chandra by detecting hard X-ray components of magnetar spectra. Together, these observatories have been instrumental in characterizing the spectral and temporal properties of magnetar outbursts. For instance, observations of the magnetar 1E 1841-045 in the KES 73 supernova remnant have provided insights into its emission mechanisms. The combined data from Chandra, Nuclear Spectroscopic Telescope Array, and other telescopes have helped model the magnetar's spectrum as a combination of thermal and non-thermal components, shedding light on the physical processes at play. Studying the magnetic behavior of white dwarfs, neutron stars, and magnetars offers more than just astrophysical insights. It provides a natural laboratory for testing the laws of physics under extreme conditions. The intense magnetic fields and densities present in these objects allow scientists to explore phenomena like quantum electrodynamics in regimes unattainable on Earth. For example, the vacuum birefringence effect, a prediction of quantum electrodynamics, where a strong magnetic field can polarize the vacuum, might be observable in the light emitted from magnetars. Detecting such effects would be a significant milestone in confirming aspects of quantum theory. Moreover, understanding the magnetic field evolution in these compact objects can inform models of stellar evolution, supernova mechanisms, and the behavior of matter at nuclear densities. As observational techniques advance, and as more sensitive instruments come online, our comprehension of these magnetic titans will continue to deepen, unraveling the mysteries they hold. Cosmic webs and the future of magnetism. Across the vastness of space, far beyond the glowing spiral arms of galaxies and the flickering birthplaces of stars, stretches a hidden force that binds the cosmos in ways we are only beginning to grasp. Magnetism is not confined to planets or stars. It stretches into the fabric of the universe itself, threading its way through galaxy clusters and weaving across the intergalactic medium. In this final act of our exploration, we turn to the magnetic threads that lace the cosmic web, the most elusive and expansive structures shaped by this invisible architect. Galaxy clusters are colossal structures, gravitationally bound gatherings of hundreds or even thousands of galaxies. Within these clusters lies not just visible matter, but also immense amounts of hot, ionized gas known as the intracluster medium. This gas, glowing in X-rays, fills the space between galaxies, and permeating through it is a magnetic field that, while much weaker than those found on stars or planets, plays an outsized role in shaping the dynamics of the cluster. These intracluster magnetic fields typically measure a few microgauss in strength comparable to the average galactic magnetic field, but they extend across millions of light-years, making them vast in scope and influence. The origins of these cluster-scale magnetic fields are not fully understood. Some theories suggest that they are relics of the early universe, primordial fields amplified by gravitational collapse and turbulence. Others propose that galaxies inject magnetized plasma into the intracluster medium through winds and jets, seeding the space between galaxies with magnetic energy. Over time, these seed fields are amplified by motions in the plasma itself, via a cluster-scale dynamo effect or through mergers and shock waves that stir and strengthen the magnetic lines. Detection of these subtle, extended magnetic fields requires sensitive and clever observational techniques. One of the most powerful tools is Faraday rotation, the twisting of the polarization angle of light as it passes through a magnetized medium. By observing polarized radio waves from distant quasars as they shine through the intracluster medium, astronomers can infer the strength and orientation of the intervening magnetic field. Another vital method is synchrotron radiation, which occurs when high-energy electrons spiral along magnetic field lines. This emission, detected primarily in radio wavelengths, serves as a beacon of magnetic activity in regions that would otherwise appear dark and empty. To probe these faint and far-reaching signals, astronomers have turned to a new generation of telescopes. The low-frequency array has already begun mapping magnetic fields in the cosmic web by detecting weak synchrotron signals between galaxy clusters, the Very Large Array. With its high-resolution radio imaging, continues to refine our understanding of magnetic interactions on smaller scales. The Atacama Large Millimeter/Submillimeter Array contributes by revealing the fine structures of magnetized dust and gas in galaxy formation zones. Yet the most ambitious of these tools is the upcoming Square Kilometer Array, which promises to revolutionize our understanding of cosmic magnetism. Square Kilometer Array, once operational, will be the most sensitive radio telescope ever constructed, with thousands of antennas spread across continents. It will survey the sky with unprecedented depth and resolution. One of its goals is to map the magnetic field of the universe on the largest scales, tracing the magnetic filaments of the cosmic web, understanding the evolution of magnetism over cosmic time, and detecting the faint whispers of primordial magnetic fields that may have formed shortly after the Big Bang. Square Kilometer Array will allow us to conduct deep polarization surveys, measure Faraday rotation across millions of background sources, and study synchrotron emission from even the most diffuse intergalactic structures. Magnetic fields are not passive players in the cosmos, in the intergalactic medium. They guide the movement of plasma, influence the propagation of cosmic rays, and help regulate the thermal properties of gas during the formation of galaxies. These fields can shape the inflow of matter, determine where stars are born, and suppress or trigger star formation depending on their configuration. In galaxy clusters, magnetic fields help stabilize the intracluster medium against gravitational collapse, influence the morphology of radio relics and halos, and affect the mixing and transport of heat and metals across vast distances. Moreover, Magnetic fields may be key players in the cosmic feedback loop, the cycle through which energy is transferred from black holes and massive stars back into the galactic and intergalactic environment, jets from active galactic nuclei, shaped and powered by magnetic forces, inject both energy and magnetic flux into the surrounding medium. This feedback helps regulate galaxy growth, limits the cooling of gas in clusters, and seeds the intergalactic medium with both heavy elements and magnetic fields. Thus, the magnetic field acts as a channel for energy redistribution on a cosmic scale. Philosophically, the study of cosmic magnetism invites us to reconsider the nature of the universe itself. Magnetism, invisible to the eye yet ever present, serves as a metaphor for the hidden structures that govern the cosmos. Its subtlety masks its strength, and its ubiquity is easily overlooked, yet it holds galaxies together, protects planets, sculpts stellar nurseries, and may even connect us to the earliest moments of creation. The more we peer into its patterns, the more we recognize its role as one of the silent shapers of existence. There is also a melancholic beauty to this story. Magnetic fields are transient on cosmic timescales. They evolve, decay, and vanish as stars die. Galaxies merge, and the universe expands, yet they leave behind traces, echoes in the radiation, patterns in polarization, subtle bends in the paths of particles that testify to their presence long after they are gone. In this way, they remind us of the impermanence of even the most powerful forces, and of the importance of listening closely to the universe's quietest whispers. As we enter an era of precision cosmology, magnetic fields will no longer be sidelined as secondary phenomena. They are emerging as central players in our understanding of the universe, linking the microphysics of particles to the macro scales of structure formation, from the heart of magnetars to the filaments of the cosmic web. Magnetism pervades every level of reality. And as we map its influence, we gain not only knowledge of the forces at work, but also a deeper sense of our place in this grand and mysterious universe. As we come to the end of this journey through the unseen architecture of the cosmos, we're left with a new appreciation for something so invisible, so silent, and yet so powerful. Magnetic fields are not just lines on a diagram or abstract forces in physics equations. They are the breath between stars, the sculptors of galaxies, the protectors of worlds, the whisperers of origin stories written not in words, but in charged particles and cosmic light. We've traced them from the molten hearts of planets to the glowing arms of spiral galaxies, from the crackling surface of magnetars to the tangled threads of the intergalactic medium. We've seen how they guide cosmic rays, shape jets that erupt from black holes, regulate the birth of stars, and protect fragile atmospheres on distant worlds. They carry memory and momentum. They weave through time. And yet, for all we now know, magnetic fields still leave us with questions as vast as the space they move through. What gave birth to the universe's first magnetic field? Was it seeded in the furnace of the Big Bang, or did it arise from deeper laws still waiting to be discovered? Why do these fields persist in patterns so intricate and coordinated across billions of light years? Is magnetism merely a consequence of charged motion, or is it a fundamental rhythm of the cosmos, a beat we have only just begun to hear? There is something profoundly humbling in the realization that all around us and within us, magnetism flows. Our own Earth is wrapped in its shield. The sun's storms reach out to us through it. Even the magnetic atoms in our blood once danced to the field lines of ancient stars. It reminds us that we are not separate from the cosmos. We are threaded into it. Our instruments: square kilometer array, low frequency array, Atacama, large millimeter array. The Event Horizon Telescope are tuning into the whispers of these fields with growing clarity. Soon, we may map them not just in patches, but across the full tapestry of the cosmic web. We may use them as tools, as timekeepers, even as probes into physics beyond the standard model. They may one day tell us about the symmetry of the vacuum, about hidden particles, about the very fabric of space-time. But more than that, magnetic fields connect us to the poetry of the universe. They are the invisible ink that shapes galaxies, the geometry that guides the dance of matter, the memory of movement long past, and perhaps, just perhaps, the signature of something deeper still. In a world that is so often loud, it's fitting that the universe holds its structure together with something quiet. So the next time you look up at the night sky, remember this: what you see is only part of the story. Behind the light, behind the stars, lies an intricate lattice of magnetism stretching across the void, binding the galaxies, pulsing faintly in the dark. This is the music of the cosmos. This is the voice of the invisible. And it is still being written. Thank you for joining this exploration of the cosmic magnetic field. If this journey sparked wonder, leave a comment, subscribe, and share it with someone curious. The universe is waiting.
What if I told you that deep within the cosmos, there exist celestial objects so dense that a mere teaspoon of their matter outweighs entire mountains? What if I said that some of these objects spin hundreds of times per second, firing beams of energy into space like cosmic lighthouses? These are neutron stars, stellar remnants of unimaginable violence, and among them, pulsars stand as some of the most extreme entities in the universe. But where do they come from? And how have they shaped the very fabric of our galaxy? Deep within the constellation Taurus, some 6,500 light-years from Earth, lies one of the most breathtaking remnants of a stellar explosion, the Crab Nebula. Listed as the very first entry in the Messier catalog, this vast cloud of interstellar gas has fascinated astronomers for centuries. It was first recorded in the 18th century, but its true origins trace back much further, nearly a millennium earlier, to the year 1054, when a brilliant supernova erupted, briefly outshining the entire night sky. Over the centuries, as our understanding of the cosmos deepened, astronomers began to suspect that something extraordinary lay hidden within the heart of the nebula. By the late 1960s, with the advent of radio astronomy, their suspicions were confirmed. Nestled within the remnants of the ancient supernova was an object both small and supremely powerful, a neutron star, spinning rapidly and emitting pulses of radiation with clockwork precision. This was a pulsar, one of the most enigmatic and extreme celestial bodies ever discovered. Neutron stars do not arise from ordinary stars like our Sun. Instead, they are born from the fiery depths of massive stars, collapsing under their own immense gravity in the final moments of a supernova. The result is an object so dense that it defies human comprehension, teetering on the very edge of becoming a black hole. Yet, far from being mere relics of destruction, these pulsars play a fundamental role in enriching our galaxy with the building blocks of life. The story of a neutron star begins in the heart of a dying giant, a star that has exhausted the nuclear fuel that once sustained its brilliance. For stars like our Sun, this conclusion is a gentle transition. They shed their outer layers and settle into a stable white dwarf state, no longer fusing elements but still glowing with residual heat. However, for more massive stars, those with at least 10 times the mass of our Sun, the end is far more dramatic. These behemoths do not simply fade away, they explode in one of the most cataclysmic events in the universe, a supernova, a detonation so powerful that for a fleeting moment it can outshine an entire galaxy. As a massive star nears the final stages of its life cycle, it undergoes a series of increasingly desperate nuclear reactions, burning through heavier and heavier elements in a futile attempt to sustain itself. Hydrogen fuses into helium, helium into carbon, carbon into neon, neon into oxygen, and so forth, until the core is composed of iron. Unlike previous fusion reactions, the fusion of iron does not release energy, it consumes it. This marks a turning point in the star's fate. With no outward radiation pressure to counteract gravity, the iron core succumbs to its own immense mass. The outer layers, no longer supported by fusion, crash inward, compressing the core at velocities approaching a significant fraction of the speed of light. In an instant, the star's core, once spanning thousands of kilometers, shrinks to a diameter of mere tens of kilometers, while the infalling layers rebound off this newly formed ultra-dense object. This rebounding energy triggers a supernova explosion, blasting away the outer layers into interstellar space while the core remains behind. What happens next depends on the remaining mass of this stellar remnant. If the collapsed core retains more than approximately 3 times the mass of the Sun, gravity is too powerful for any known force to resist. The collapse continues indefinitely, crushing matter into an infinitely small singularity, a black hole, an abyss from which not even light can escape. But if the core's mass is below this critical threshold, a different fate unfolds. The collapse halts, not because of thermal pressure, as in ordinary stars, but due to a remarkable quantum mechanical effect known as neutron degeneracy pressure. This phenomenon arises because neutrons, like electrons, are fermions. They obey the Pauli exclusion principle, which states that no 2 identical fermions can occupy the same quantum state simultaneously. As the core contracts, free electrons are squeezed so forcefully into atomic nuclei that they merge with protons, forming an abundance of neutrons. These neutrons, in turn, resist further compression through degeneracy pressure, stabilizing the core against complete gravitational collapse. The result is a neutron star, an object of almost inconceivable density. A neutron star is no ordinary stellar remnant. It compresses up to 2 solar masses into a sphere only 20 to 25 kilometers wide, roughly the size of a metropolitan city like Boston, Frankfurt, or Cincinnati. The density of such an object is staggering. A single teaspoon of neutron star material would weigh over 1 billion tons on Earth. This is because neutron stars are composed almost entirely of nuclear matter, a state of matter even denser than atomic nuclei. With such extreme compression comes an equally extreme gravitational field. The escape velocity from a neutron star's surface exceeds half the speed of light, meaning anything that ventures too close would need to travel at relativistic speeds to break free. The curvature of spacetime around such a dense object causes gravitational time dilation, a phenomenon predicted by Einstein's general relativity, where time itself slows down in the presence of intense gravity, similar to, but not quite as extreme as, the effect near a black hole. The outer crust of a neutron star, though only a few kilometers thick, is one of the hardest substances in the universe, made up of an iron lattice interspersed with degenerate electrons. This rigid crust encases the unimaginable chaos beneath it. The temperatures here can reach hundreds of millions of degrees Kelvin, with some neutron stars, like RxJ 1856.5 3754, radiating at nearly 500,000 Kelvin even after millions of years. Beneath this crust lies an even stranger layer, nuclear pasta. Here, under crushing pressure, neutron-rich matter arranges itself into bizarre, spaghetti-like structures, forming the densest known material in the universe. Deeper still, the core is thought to consist of a superfluidic mass of bulk neutronium, where neutrons flow without resistance, generating effects that defy classical physics. Some theories even suggest that within the deepest reaches of the core, matter may transition into an exotic quark-gluon plasma, where individual neutrons and protons dissolve into their fundamental quark constituents. Neutron stars possess the strongest magnetic fields known in the cosmos. The conservation of angular momentum during the collapse dramatically amplifies the progenitor star's magnetic field, concentrating it into a volume thousands of times smaller. As a result, some neutron stars, known as magnetars, exhibit fields trillions of times stronger than Earth's, capable of distorting atomic structures and even influencing quantum vacuum fluctuations. These magnetic fields are responsible for a host of extreme astrophysical phenomena, from high-energy X-ray bursts to magnetar flares that release more energy in a fraction of a second than the Sun emits in 100,000 years. Not all neutron stars remain as quiet stellar corpses. If a neutron star is spinning rapidly and emits beams of radiation from its magnetic poles, it becomes a pulsar, one of the most extraordinary cosmic lighthouses. As the neutron star rotates, these focused beams sweep across space, appearing as regular pulses of light when viewed from Earth. Some pulsars, like PSRJ 1748-2446 AD, spin at nearly 716 times per second, meaning their surfaces move at nearly a quarter of the speed of light. Pulsars are among the most precise clocks in the universe, their rotational periods so stable that they rival atomic clocks in accuracy. They have been used for a range of scientific applications, from testing general relativity to aiding in the search for gravitational waves. Some pulsars even exist in binary systems, spiraling toward companions in a cosmic ballet that provides invaluable insights into relativistic physics. Neutron stars are more than just relics of stellar deaths. They are laboratories of the extreme, where physics is pushed to its absolute limits. Their immense densities, powerful magnetic fields, and relativistic phenomena make them crucial to our understanding of the fundamental forces governing the universe. They enrich galaxies with heavy elements, contribute to the cosmic web of radiation, and serve as cosmic signposts, guiding our understanding of gravity, quantum mechanics, and the nature of matter itself. Through the lens of modern astronomy, these exotic stellar remnants continue to unveil secrets of the universe, one pulsating beacon at a time. Within the extreme environment of a neutron star's magnetosphere, charged particles are forced to follow the paths dictated by intense magnetic field lines, riding along flux lines as they are funneled toward the star's polar caps. However, upon reaching these regions, they experience rapid repulsion, resulting in their expulsion at relativistic velocities. This acceleration process induces the emission of synchrotron radiation, which manifests predominantly in the radio wavelengths of the electromagnetic spectrum. One of the most fascinating aspects of pulsars is their role as cosmic lighthouses. The misalignment between a neutron star's rotational axis and its magnetic poles causes these beams of radio energy to sweep across space, much like the spinning beacon of a lighthouse. If Earth happens to be in the path of these periodic emissions, we observe them as highly regular pulses of radio waves. The first confirmed evidence of neutron stars in nature emerged through the detection of these pulsating radio signals. This breakthrough occurred in 1967 when Jocelyn Bell Burnell, a postgraduate student at the University of Cambridge, detected a series of galactic pulses occurring precisely 1.3 seconds apart. The discovery initially baffled the scientific community, with some even entertaining the possibility that the signals were artificial in origin, perhaps communications from an extraterrestrial intelligence. However, as more such signals were identified, including one emanating from the heart of the Crab Nebula, a natural astrophysical explanation began to gain traction. Theorists soon converged on the idea that these rapid radio pulses originated from rotating neutron stars. Their compact nature, extreme densities, and rapid spin rates made them the only viable explanation for such precise, high-frequency emissions. Since then, radio pulsars have become one of the most well-documented classes of neutron stars, with over 3,200 pulsars catalogued across the Milky Way. However, given the estimated number of supernovae that have occurred over the 13.6 billion-year history of our galaxy, it is believed that at least 1 billion neutron stars still exist within the Milky Way, and countless more in galaxies beyond. Most of these, however, have long since cooled and slowed, making them undetectable to us. Neutron stars, particularly pulsars, are at their most energetic in the first million years following their formation in a supernova. If a pulsar exists in isolation, meaning it lacks a significant stellar companion, its fate is sealed by a gradual loss of rotational momentum. This spin-down process occurs as the pulsar radiates energy in the form of gravitational waves and electromagnetic radiation. The immense magnetic field of the pulsar interacts with the surrounding space, dragging and distorting it. Over time, this interaction transfers kinetic energy away from the star's rotation, resulting in a progressive slowdown of its spin rate. This spin-down process governs the diverse spectral emissions of neutron stars. Younger, more energetic pulsars predominantly emit radio waves, while older and more evolved neutron stars, particularly those in binary systems, can also emit in X-ray and gamma-ray wavelengths. However, for a neutron star to sustain high-energy emissions in the X-ray and gamma-ray range, it typically requires an external source of energy replenishment, namely a nearby stellar companion from which it can accrete mass. In binary star systems, this process enables neutron stars to reignite and sustain their high-energy emissions, leading to the formation of millisecond pulsars and X-ray pulsars, objects that challenge our understanding of extreme physics and the life cycle of neutron stars. From their discovery in the 20th century to their role in modern astrophysics, pulsars have not only confirmed the existence of neutron stars, but have also become cosmic laboratories for testing the laws of physics. These extreme remnants continue to illuminate the mysteries of stellar evolution, relativity, and magnetism, providing insights into some of the most fundamental forces shaping our universe. X-ray binary pulsars, the powerhouses of stellar accretion. In some cases, a neutron star does not remain isolated, but instead resides within a binary system where it shares its cosmic dance with a stellar companion. This companion, which may be a white dwarf, red giant, or even a sun-like star, continuously sheds material into space, forming an accretion disk around the neutron star. As the neutron star gravitationally siphons matter from this disk, the infalling material not only increases the neutron star's mass, but also transfers angular momentum, accelerating its spin in a process known as spinning up. These pulsars, fueled by accretion, are classified as accretion-powered pulsars or X-ray pulsars, named for their prolific emission in the X-ray spectrum. As matter from the accretion disk is funneled onto the neutron star's surface, electrons become highly energized within its intense magnetic field. These electrons spiral along field lines before slamming into the star's polar caps, where they decelerate, releasing vast amounts of X-ray radiation in the process. These emissions, concentrated into narrow beams, rotate along with the neutron star, much like the sweeping searchlight of a radio pulsar. However, unlike standard radio pulsars, which predominantly slow down over time, X-ray pulsars can exhibit both spin-up and spin-down behavior, and in some instances, they maintain an astonishingly stable rotation rate over extended periods. If the neutron star's companion is a low-mass star, such as a small red dwarf or a white dwarf, the system is classified as a low-mass X-ray binary. Conversely, if the donor star is a massive and unstable red or yellow giant, the system is designated as a high-mass X-ray binary. In both scenarios, accretion fuels the neutron star, accelerating it to extreme rotational speeds, reaching hundreds of revolutions per second. Millisecond pulsars, the fastest rotating neutron stars. When a pulsar's rotation period drops below 10 milliseconds, meaning it completes more than 100 full spins per second, it is classified as a millisecond pulsar. Also referred to as recycled pulsars, these objects represent the fastest spinning neutron stars in existence, having been spun up to near relativistic speeds by prolonged accretion. At such staggering rotational velocities, they emit exquisitely regular and precise pulses, making them valuable tools for astrophysical measurements. The incredible stability of these pulses allows astronomers to detect even the slightest perturbations in their signals. For instance, the first exoplanets ever discovered, found in 1992 around the millisecond pulsar PSRB 1257+12, were detected through minute Doppler shifts in its pulse timing. These planets remain among the smallest known exoplanets to this day, with sizes and masses comparable to Earth's moon. The discovery of the first millisecond pulsar, PSRB 1937+21, in 1982 marked a turning point in neutron star astrophysics. Spinning at an astonishing 641 revolutions per second, it held the record as the fastest known pulsar for decades. However, a more extreme object was later identified, PSR J1748-2446 AD, located within the dense stellar environment of Terzan 5. Rotating at a breathtaking 716 times per second, this pulsar's equatorial surface races through space at approximately a quarter of the speed of light. These hyperfast neutron stars are often found in globular clusters, densely packed stellar environments containing tens or even hundreds of thousands of ancient stars. In such close quarters, binary interactions are common, leading to an unusually high incidence of millisecond pulsars. The clusters Terzan 5 and 47 Tucanae hold the records for the most known millisecond pulsars, boasting 37 and 22 respectively. Despite their extreme spin rates, millisecond pulsars do not necessarily host the strongest magnetic fields in the universe. A neutron star's magnetic field strength is largely dictated by its age and progenitor star type, rather than solely by its rotation speed. Certain progenitor stars, such as the recently discovered massive magnetic helium star HD 45166, exhibit fields exceeding 100,000 times that of Earth. When such a star undergoes core collapse, its already powerful magnetic field is amplified exponentially, giving rise to the most magnetized objects in existence, magnetars. These extreme neutron stars possess fields trillions of times stronger than Earth's, capable of distorting atomic structures, altering the vacuum of space, and releasing bursts of energy so powerful that they can temporarily disrupt radio communications on Earth from thousands of light years away. As such, magnetars represent the pinnacle of neutron star evolution, bridging the gap between the already extreme properties of pulsars and the even more mysterious realms of quantum physics and general relativity. From accretion-powered X-ray pulsars to the lightning-fast millisecond pulsars and the unfathomable power of magnetars, neutron stars continue to test the limits of modern physics. As we probe deeper into these enigmatic objects, we may yet uncover new insights into the fabric of the universe itself. Magnetars, the titans of stellar magnetism. The tale of these extraordinary cosmic entities begins in 1979, when astronomers first detected an enigmatic burst of gamma radiation originating from the Large Magellanic Cloud. Unlike conventional gamma-ray bursts, this signal exhibited slightly longer wavelengths, what scientists would later call soft gamma rays, before fading into obscurity for 2 months. Then, on March 5th of that same year, the enigmatic source returned, producing one of the most luminous gamma-ray outbursts ever recorded, unleashing in a mere fifth of a second an amount of energy equivalent to 1,000 years of solar output. While neutron stars were the immediate suspects, the peculiar softness of the gamma rays and the repeating nature of the outbursts defied the behavior of conventional neutron stars. By the end of the year, 3 distinct instances of these emissions had been identified, earning them the designation soft gamma-ray repeaters. These objects exhibited periodic flashes of low-energy gamma rays that would persist for about a week before fading into dormancy, sometimes for months, even years. Yet, each active phase provided crucial insights into their underlying mechanisms, particularly their rotation rates and spin-down behavior, enabling scientists to infer their magnetic field strengths. To their astonishment, all 3 objects exhibited field strengths on the order of hundreds of trillions of Gauss, with some estimates exceeding a quadrillion Gauss, a staggering 2 quadrillion times stronger than Earth's magnetic field. These were not merely extreme neutron stars. They were the most magnetized objects ever discovered in the universe, operating at the very limits of efficiency for a spinning, radiating stellar core. Around the same time, astronomers began detecting another class of peculiar signals, this time in the X-ray spectrum. Unlike conventional accretion-powered X-ray pulsars, these objects emitted short, high-energy X-ray bursts that exhibited anomalous behavior. Over time, it became increasingly clear that these anomalous X-ray pulsars shared striking similarities with the soft gamma-ray repeaters, hinting at a common astrophysical origin. Both classes of objects exhibited extreme outbursts, transient flares, and irregular decay patterns, leading scientists to propose a new classification, magnetars. The term, coined in the early 1990s, described neutron stars with magnetic fields so strong that they could drive some of the most violent and energetic processes ever observed in the cosmos. Despite their extraordinary power, magnetars appear to be exceptionally rare, with only about 25 known examples in the Milky Way. Their scarcity likely stems from the fact that they represent a brief, transitional phase in the evolution of highly magnetized neutron stars. During this phase, a magnetar's magnetic field undergoes rapid decay, generating a host of extreme astrophysical phenomena, including magnetic reconnection events, megaflares, and intense X-ray and gamma-ray bursts. Magnetars exist in a realm beyond our typical understanding of stellar remnants. With magnetic fields trillions of times stronger than Earth's, they exert forces so extreme that they can distort atomic structures, alter the very fabric of space-time, and generate some of the most intense high-energy emissions in the universe. These objects are ticking time bombs of magnetic instability, periodically unleashing bursts that momentarily rival the brightness of entire galaxies. Starquakes, the tremors of a magnetar's fury. As dead stars rotate, their metallic crusts endure ceaseless torment, pressed between the immense forces acting from within and without. Beneath the surface, swirling currents of superfluid neutronium generate staggering electrical fields, while above, the twisting and dragging of intense magnetic field lines exert enormous tension. Over time, this relentless stress proves too much for the crystalline crust of the neutron star. Eventually, it cracks, just slightly, shifting by mere micrometers toward a more spherical configuration. But in the world of magnetars, even such imperceptible shifts can unleash some of the most violent electromagnetic events in the cosmos. These seismic readjustments, known as starquakes, release torrents of electromagnetic radiation, including bursts of high-energy X-rays and soft gamma rays. The most extreme starquake ever recorded occurred on December 27, 2004, when the magnetar SGR 1806-20 produced an eruption so powerful that in under 1 second, it emitted more gamma-ray energy than our Sun generates in 150,000 years. Despite the fact that this event occurred over 40,000 light-years away, its impact was still felt on Earth. The trailing shock waves of radiation were so intense that they caused a detectable increase in ionization levels in our planet's upper atmosphere. Had such an outburst occurred within 10 light-years of Earth, the consequences would have been nothing short of catastrophic. The immense gamma radiation would have completely eroded our magnetic field, leaving the planet exposed to the full onslaught of solar radiation. This, in turn, would have boiled away the oceans, stripped the atmosphere, and transformed Earth's surface into a parched, irradiated wasteland, a world bereft of life. Yet gamma rays are not the only emissions thought to arise from starquakes. Some researchers have proposed that these seismic events may also be a potential source of fast radio bursts, brief yet highly energetic radio pulses that have baffled scientists since their discovery. To date, over 700 of these enigmatic signals have been recorded with no definitive explanation for their origin. Intriguingly, at least 30 of these FRBs are classified as repeaters, signals that, while not constant, appear sporadically from the same location. This recurrence suggests a possible link between FRBs and magnetar activity, drawing a potential parallel to the soft gamma-ray repeaters emitted by these stars. Alternatively, some astrophysicists speculate that fast radio bursts might be produced during the violent collisions of neutron stars. In such catastrophic mergers, two ultra-dense stellar remnants crash together and consume one another, unleashing yet another level of cosmic devastation. The resulting explosions and gravitational distortions could, in turn, generate bursts of radio waves that propagate across the universe, carrying with them the faint echoes of their cataclysmic origins. Whatever their true cause, starquakes and the bursts they produce remain some of the most extreme astrophysical phenomena in existence. As observational techniques improve, future discoveries may bring us closer to unraveling the mysteries of these stellar tremors, shedding light on the inner workings of the most magnetic and volatile objects in the universe. The fastest spinning pulsars are not just celestial timekeepers. They serve as remarkably precise indicators of their surrounding environment. This property led American physicists Joseph Taylor and Russell Hulse to make a groundbreaking discovery in the early 1970s, earning them the 1993 Nobel Prize in Physics. Their work on the pulsar PSRB 1913+16, a rapidly spinning neutron star locked in a binary system with a slower, cooler neutron star companion, provided the first indirect observational evidence for gravitational waves, a phenomenon predicted by Albert Einstein nearly 80 years earlier. By measuring the Doppler shifts in the pulsar signal, Taylor and Hulse demonstrated that the two neutron stars were spiraling ever closer together, losing energy through the emission of gravitational waves, invisible ripples in the very fabric of space-time. It would take another 30 years before humanity would achieve the first direct detection of these waves in 2015, using the Laser Interferometer Gravitational Wave Observatory. When two compact stellar remnants, whether black holes, neutron stars, or a combination of both, spiral toward each other, their orbital velocities increase to astonishing levels, eventually reaching speeds of 2/3 the speed of light. The rapid motion of these dense objects distorts and stretches spacetime, releasing a final crescendo of gravitational waves that ripple outward across the cosmos. These signals, detected by LIGO and other observatories, often precede a cataclysmic merger, allowing astronomers to pinpoint the precise location of these cosmic collisions. As the neutron stars draw closer, the extreme gravitational forces cause them to deform, their iron-rich crusts rupturing as they near their inevitable collision. At the moment of impact, an enormous explosion occurs, scattering fragments of neutron-rich material into space and briefly exposing the shattered cores of these stellar remnants to the near vacuum of space. This event is known as a kilonova, one of the most energetic and transformative astrophysical phenomena in the universe. The crucible of heavy elements, how kilonovae forge the building blocks of planets and life. Much like a supernova, a kilonova is an extreme explosion that produces vast amounts of heavy elements. But unlike a supernova, which primarily synthesizes elements up to iron, kilonovae are responsible for the formation of the heaviest elements in the periodic table. As neutron-rich ejecta are violently expelled into space, nuclear reactions known as the R process and P process take place, enabling the synthesis of elements such as gold, platinum, uranium, and thorium, substances crucial not only for planetary formation, but also for the chemistry of life itself. For decades, astronomers believed that supernovae were the primary factories of heavy elements. However, recent discoveries suggest that kilonovae contribute the lion's share of these essential building blocks, enriching the interstellar medium with the raw materials needed to form planets, moons, and even organic molecules. Just as supernovae are associated with long-duration gamma-ray bursts, which last anywhere from a few seconds to several minutes, kilonovae produce their own class of GRBs. These short gamma-ray bursts last 2 seconds or less, a result of the brief exposure of the neutron star's shattered interiors to space. In some cases, kilonovae also emit fast radio bursts, anomalous, highly energetic radio pulses whose origins remain enigmatic. The remnants of the two neutron stars rapidly collapse into a single composite object, with its fate dependent on the combined mass of the merging bodies. If the total mass exceeds 2.5 to 3 times the mass of the Sun, gravitational collapse continues unabated, resulting in the formation of a new black hole. If the mass falls below this threshold, the merged body stabilizes into a newly formed, heavier pulsar, or perhaps a magnetar, reigniting the evolutionary cycle of neutron stars. However, if the mass lies precariously between these two extremes, an entirely different scenario may unfold. If the post-merger remnant is massive enough to overcome neutron degeneracy pressure, the force preventing neutrons from collapsing under their own gravity, but not quite massive enough to reach black hole status, then the result is a boundary object, teetering on the edge of known physics. Under these incomprehensible pressures, neutrons themselves dissociate into their fundamental quark components, potentially forming an exotic quark star, an entity whose structure may resemble the extreme conditions of the early universe moments after the Big Bang. Neutron star mergers offer a rare, natural laboratory for probing these extremes of matter and energy, allowing scientists to test the limits of general relativity, nuclear physics, and quantum chromodynamics in ways previously unimagined. The discovery of such boundary objects could reshape our understanding of the very nature of matter and space-time itself. The merging of neutron stars is more than just a spectacular astrophysical event. It is a cosmic alchemy, responsible for forging the heaviest elements, sculpting the interstellar medium, and shaping the very fabric of the universe. From the gravitational waves that ripple across space-time to the kilonovae that paint the cosmos with elemental richness, these collisions leave an indelible mark on the past, present, and future of the cosmos. Quark stars, the hypothetical realm of subatomic stellar remnants. Neutrons, the fundamental components of atomic nuclei, belong to a class of particles known as hadrons, composite subatomic particles made of quarks bound together by the strong nuclear force. Quarks are the most elementary building blocks of matter. They possess no internal structure and cannot be broken down further by pressure or heat. These elementary particles emerged in the primordial moments of the universe, when temperatures and densities were unfathomably high. However, as the universe expanded and cooled, free quarks coalesced into hadrons, forming the protons and neutrons that now constitute ordinary matter. Though free quarks are no longer found in nature, they could theoretically exist in an ultra-compressed state of matter, a scenario hypothesized to occur within a quark star. Such an object would form when an accreting neutron star approaches the Tolman-Oppenheimer-Volkoff limit, the critical threshold where gravitational collapse is strong enough to overcome neutron degeneracy pressure. In this extreme environment, the very structure of neutronium could break down, leading to quark deconfinement, a process in which neutrons themselves dissolve into a quark-gluon superfluid. This exotic state of matter, held apart by its own nuclear repulsion against gravity, would give the star a density comparable not to an atomic nucleus, but to a hadron-sized entity on a macroscopic scale. A two-flavor quark star, composed solely of up and down quarks, would resemble a neutron star in many ways, with a dense quark-gluon core surrounded by an outer shell of less pressurized nuclear matter. Its maximum diameter would likely be around 15 kilometers, akin to that of a typical neutron star. However, if a quark star were to contain an additional component, strange quarks, which belong to the second generation of fundamental particles, the composition of the star would be drastically altered. Strange quarks share the same charge as down quarks, yet their presence allows for additional nuclear conversions, potentially making the star significantly more stable in low-energy states. In fact, some theoretical frameworks propose that strange quark matter may represent the absolute ground state of matter at the highest densities, meaning that a three-flavor strange quark star would be self-bound, requiring no solid nuclear crust to maintain its integrity. Instead, it would possess a transient, fluctuating boundary, a thin interface where quark density abruptly falls to zero. In its early stages, a strange star would lack a solid outer crust. Over time, however, intense electrical currents emanating from its quark core would expel the remnants of normal nuclear matter, forming an ephemeral, decoupled shell. This outer layer would be short-lived, as periodic collapses back into the star would catalyze immense bursts of electromagnetic radiation, including gamma-ray flares. Such emissions have been proposed as a potential explanation for anomalous soft gamma-ray repeaters, high-energy bursts that deviate from conventional magnetar activity. Following each outburst, the bare strange quark core would once again be exposed to the vacuum of space, leading to a cyclical process of violent emissions. Furthermore, because strange quark matter is theoretically extremely stable, any fragments ejected from the star could persist indefinitely as free-floating particles, nuggets of strange quark matter known as strangelets. Despite their theoretical plausibility, quark stars and strange stars remain hypothetical, as no confirmed observational evidence has yet validated their existence. From a distance, these objects would likely be indistinguishable from conventional pulsars, making their identification extraordinarily difficult. While quark stars remain an intriguing possibility, future advancements in observational astrophysics may provide the key to their detection. Some astronomers speculate that objects like GOJ 165540, a known X-ray binary with unusual characteristics, could hint at the presence of a hybrid neutron-quark object. As research continues, instruments capable of resolving quark-level astrophysical signatures may someday provide empirical confirmation of these enigmatic stellar remnants. Thornitko objects, the star within a star. Among the most enigmatic and rare stellar configurations ever theorized is the Thornitko object, a peculiar hybrid star where a neutron star is engulfed by the immense envelope of a red giant. First proposed in 1977 by Kip Thorne and Anna Zhitkow, these objects blur the line between conventional stellar evolution and extreme astrophysical phenomena, challenging our understanding of the interactions between compact remnants and their larger, living stellar companions. A prime candidate for such an origin story is the system formerly known as X-ray Nova Scotia 1994, a chaotic binary system located 10,000 light-years away. At its heart lies a small evolved F-type star, locked in a volatile gravitational dance with an unseen accreting companion, inferred to be a black hole several times the mass of the Sun. The unusual dynamics of this system, its tight orbital period and high velocities, suggest that both objects share a common progenitor, likely tracing their history back to a hybrid star that once hosted an infalling neutron star. Unlike typical binary interactions, where a neutron star may tidally disrupt or accrete matter from its companion, a TO emerges when a neutron star spirals inward into the extended envelope of a red giant. Rather than tearing its companion apart, the neutron star plunges beneath the giant's photosphere, sinking into its interior while remaining intact. This marks the formation of a true star within a star. Over the next few hundred years, the neutron star continues to migrate inward, pulling intense magnetic fields and gravitational perturbations through the plasma of its host. This interaction violently disrupts the delicate balance of the red giant's interior, causing instabilities in its core structure. Despite this turmoil, the object's external appearance remains largely indistinguishable from a conventional late-stage red giant, making direct detection an ongoing challenge. Within a TGO, the neutron star and the disturbed stellar core eventually enter a tight orbit, triggering a final, catastrophic merger. When this happens, the vast majority of the red giant's mass is funneled into the forming black hole, while its outer layers, now left without an internal energy source, collapse and disperse into space. However, not all of this material is lost to the abyss. It is hypothesized that some residual stellar matter survives, condensing into what is now observed as a curiously low-mass, evolved F-type star. This peculiar survivor, still orbiting and feeding the black hole, may provide an observational signature of past Thorne-Jitko evolution. Beyond their sheer astrophysical intrigue, Thorne-Jitko objects illustrate the profound and often unexpected contributions of neutron stars to the wider galactic ecosystem. Though these objects exert destructive gravitational forces, their dynamic interactions also enrich surrounding space with complex chemical elements, the raw materials necessary for planet formation and the emergence of life. In this sense, neutron stars, despite their seemingly hostile and inexorable nature, have played a vital role in shaping the universe as we know it. Their interactions, whether through supernovae, binary mergers, or the creation of objects like TOs, have helped seed galaxies with the ingredients essential for organic chemistry and planetary development. Thus, the discovery of such objects may be just as significant to modern astrophysics as it would have been had the first pulsar signal, LGM-1, truly been an interstellar transmission from extraterrestrial intelligence. In the grand scheme of cosmic evolution, these fascinating stellar remnants continue to illuminate the unknown, shaping the very conditions that make life possible. And with that, we close this chapter on the unfathomable complexity of the cosmos.